Welcome back, Chemistry 30. This is the last booklet in Unit 2, 16.5, Reaction Spontaneity. So here we'll look at what a spontaneous process is, entropy, law of disorder, and free energy. We'll look at identifying how entropy affects influence chemical reactions. Consider the the interaction between enthalpy and entropy to determine whether a reaction is spontaneous or not. Use the concept of free energy to express the relationship between entropy and enthalpy, and then predict if a reaction is spontaneous or not by using this relationship here. So first of all, spontaneous. A spontaneous process is a chemical or physical change that occurs without outside intervention given the environment. So if we're talking about room temperature, a reaction could be spontaneous at room temperature given that condition. So with most reactions, you need a little bit of energy to start it, and then it will continue on without any other intervention. So for example, iron rusts automatically when it's outside in the elements, or at room temperature again, melting ice. Ice melts naturally at room temperature. It's a spontaneous process. So based on earlier things that we talked about, spontaneous reactions were thought to be, all of them were exothermic, because you're going from a high energy reactant to a lower energy product, releasing heat. You're going to a lower energy state. In life, we like to go to a lower energy state, so it seems that that would make sense. But of course, you don't have to look too far to find an example to the contrary. Melting ice is endothermic. It requires the addition of heat. So there must be something else involved with whether or not a reaction can occur spontaneously. And that factor is entropy, which measures how disordered something is. So spontaneous reactions also look at entropy, and it looks at going in a direction that causes the entropy of the universe to increase, to be disordered. And you can look at, like cleaning up your room, doesn't take too long for it to get a mess again. Or the TV show Hoarders is another example. Things get out of hand very quickly because the universe tends to like that direction. In a chemical reaction, entropy, the symbol for entropy is S. So to figure out the entropy of the system, you're looking at the entropy of the products, the entropy of reactants. So once again, what happens before, what happens after. The difference is what we're looking at after compared to what we had initially. So if the entropy of the products is bigger than the entropy of the reactants, that means we're getting more disordered. The entropy value is a positive number. It's big. That means more disordered. For example, if you take a deck of cards and throw them everywhere, before, it was in a card deck. After, spread all over the floor, so that's more entropy. If you look at vice versa, when we have our entropy of reactants bigger than products, we would get a negative value for entropy overall. That means the product value is less than the reactant, which means things are getting more ordered or less disordered. So playing cards back in the pack would be an example of causing things to be in an ordered state, lower entropy. So there's many different things we can look at here. What makes high entropy or low entropy? The first one, physical state. The entropy of a gas is bigger than entropy of a liquid, which is bigger than entropy of the solid. Makes sense because this is more disordered. It's hard to contain a gas. Liquid, you can somewhat contain it by putting it in a glass or a bowl. But it's more disordered than, let's say, a solid brick just sitting on the table. So high entropy, high disorder, low entropy, more ordered state. So you're going from random to more ordered. Dissolving a gas in a liquid decreases entropy because it's making it into an ordered state. You have to force that gas to be in there. Just like a soda stream machine, you are forcing gas to be in the liquid. You're making it an ordered state. It doesn't naturally want to do that. So put gas dissolved in liquid, that is low entropy. So as I mentioned here, gas in liquid is more ordered. It was forced to be there. Okay. Assuming no change in physical state, the entropy of a system will increase if you can make more gas particles. So the side that has the more gas particles is the more entropy, the more disordered, because gas is all over the place. More molecules, more randomness, more heating, etc. Dissolving a solid in a liquid, however, you're taking something that's like a solid sugar cube and dissolving it. It's getting more spread out, more disordered, more random, so it is entropy increasing. So when you take solid particles, spread them out, in the process of dissolving, entropy increases. Of course, increasing temperature causes increased movement. Particles move faster, hit harder, etc. So that is increasing entropy. You're increasing the randomness. Then I have a few examples here. So predict the sign of the entropy of the system for the following and state your reasons. So here, this is basically the formation of water equation. And all those factors that we talked about, I think it's the one about we don't have a change in state, we don't have a gas and a liquid, but we have this happening. We have a different number of gas molecules on each side. On the left-hand side, you can see I have 3 molecules of gas, 2 hydrogen, 1 oxygen. On the right-hand side, I have 2 molecules of water. So the entropy is decreasing as we go from left to right because products are less than reactants. So it would be a case like this, products less than reactants, it's more ordered, so we would have entropy decreasing because we have fewer molecules on the right hand side. Or we could say the entropy of the reactants is higher than the products. Over here, all of these are the example of changes in physical state, such as over here. So it doesn't matter what substance you have. Gases are more random than liquids, so higher entropy. Solid to gas, gas is higher entropy, or solid to liquid, higher entropy. So we would say the entropy of this reaction is decreasing, going left to right, and entropy of these is all increasing because the increased entropy item is on the right hand side. What must be true about entropy of the universe? In order for a reaction to be spontaneous, it must increase. And so that the two things that we've looked at here, if we can make the entropy of the system increase, that's going to favor a spontaneous reaction. Also, exothermic reactions, ones that achieve lower energy states, are also favorable where spontaneous reactions are concerned. So that's a key thing to point, those two things. And looking at relating these two things brings us to the last part of the booklet, and that is looking at the Gibbs free energy, which is really energy available to do useful work, but we're using it to figure out whether a reaction is spontaneous or not by looking at the entropy value and the enthalpy value. Now, I have quite a few things to go over yet, and we're almost at the end of the video for time-wise, so we'll do that in part 2. Okay, so we'll see you soon.